closer to the secondary creep. Number 5, well, that's way and beyond. For instance, exceeding limits shown, engine would be stripped. So anything above that, the compressor should never get faster than that at all because of the fail-safe scenarios. But again, if they've failed for whatever reason, and the engine has gone way faster than that, then I think we're in the engine's going to get stripped down and replaced anyway. So that's just a typical graph. Again, it will be more specific to the engines you are working on. So looking at that, we're going to look at engine health monitoring. Basically, keep an eye, like you go to the doctor, get checked up on. We also check the engine by sampling fuels, oils, borescope inspections, soap sampling, and all the good stuff as well. So let's have a look at what we might have. What we've seen already, MCDs or magnetic chip detectors again, or magnetic plugs again in the scavenge line. So any particular debris that's once the oil is going to the bearings, the bearing could be starting to breaking down. It could be the bearing itself, it could be the cage of the bearing, it could be a bit of the housing it's in. Those little bits of debris float down through the scavenge line, and the magnetic chip will pick it up, and you can use that for diagnostic purposes. Okay, so it's one of the areas I used to work in as well. We'd visual check it. If it's more extreme than normal, we'd actually prioritise that chip to be detected. We put it in a microscope once we've cleaned it, then put it on what's called a carbon disc, a little sticky disc, and that disc would go into a special electronic microscope. And this is where it zooms into lots and lots of magnification to the point, if you were to put a fly in there, you could actually look at the cells of a fly's eye. That's how extreme it was. And it can actually tell you by the calibration in that electron microscope what material it is, what that metal is. And once you define what the metal is and how much it is, it can tell you exactly what part of the bearing, the cage, it's come off from. And if it's more normal, we would have to maybe induce more samplings. Filters are a good indication of what's going wrong. Your coarse filters at the start of especially your oil system, if that's got debris already, has the oil system been contaminated by maybe debris from within a container or something else? But again, once you've got filters in the scavenge line, so the scavenge filters, they can provide some good information. Your last chance filters at the bearings, again, in theory, should be no debris there, but there might have been something like disconnected the pipe, a little bit of dirt has got in there, and that can give us an idea of what's going on. Fuel filters as well. Fuel filters can give us some indication of what's going on with the engine as well. I had a scenario on a Friday where a filter was getting replaced, just standard procedure, and we found some blue material on there which wasn't normal. So because it wasn't normal, they grounded all the aircraft. So you're looking at 30 odd aircraft on a Friday were grounded, and we had to defuel all the aircraft all that following week, refuel them, ground run them, test the filters. And what it was the Bowser driver had cleaned his nozzle for the refueling the aircraft, and a little bit of debris of the cleaning material, the bit of paper, had stuck to the nozzle and then gone inside the fuel tank. So when it came to one aircraft, it got stuck on the aircraft. But because we couldn't say where it had come from or where it was going, had it affected any aircraft, every single aircraft had to be defueled. So the Bowser I got told, next time you clean the nozzles, make sure that it's clean. All right, don't just do a quick wipe. So that caused a lot of work for no reason at all. But again, it wasn't normal. It wasn't typical sort of, what's this substance? We couldn't identify initially, so we could get tested to find out what it was. Then we've got a spectrometric oil analysis program, or SOAP for short, and that's where we take a sample of oil. Okay, we heat it up and check the wavelength. Vibration monitoring survey, again mentioned that yesterday, and the aircraft integrated data system. Okay, so we've got lots and lots of information we can look at to find out any health of what's going on with there. Again, the combination of everything, we download all this. Oh, let's come back in now. All right. Okay. Flight deck indicators. Yeah, going to need those for checking bits and pieces. Again, use monitor engine parameters such as thrust, power, RPM, all good things. So we've got live feedback of what's actually happening in front of your eyes. Ground indicators, so yeah, we'll get the bore scopes in there, your MCDs, oil filters, etc. Again, with the magnetic plugs and chip detectors. Debris monitoring system as well, what's called DMS, debris monitoring system, of how much debris is building up. Again, you can use that for diagnostics. So magnetic chips detector, we've looked at those already. Okay, just the magnets, which will be fitted in the scavenge return line. This one's a fuzz burner because we've got electrical connection here. Okay, so again, what we mentioned yesterday about a fuzz burner, this type can actually heat up the debris and burn it away. And if it comes back again, well, that's a good indication that there's more debris in the system that shouldn't be there. So it's probably worthwhile you have to resample maybe in a short time period, or actually bring the aircraft down and get it down before something actually happens, especially on helicopters. Okay. Debris monitoring system, or DMS as we call it. New additions to airfield detection systems, engine oil systems, comes from chip detectors, not to be confused with MDC ones. New system develops from Eaton Airspace. It's not a new system, it's been around for quite a long time. It will collect the debris like a magnet, and the more debris it builds up, the more resistance, and that will give a signal and to a scan sensor, and that will, you can download the information, engine management unit or health of unit management system, and we can actually determine how much debris is in the system, and it will give a limitation. You're allowed so much debris per so many flying hours. The engine we used to work on, the RB199, the magnetic chip detectors would be processed with a microscope. The debris ones, for the gearboxes and all that sort of thing, we would put onto this DMS system. And basically, again, like the normal engine ones, we put a little carbon disc, put it through a special machine, and it would count how much debris was on that particular chip. And it had to be within a certain amount. Okay, and always with a certain amount. And then we use it for trend analysis. If that was getting worse or stayed fine, that would be all good. And we would monitor that. Okay, we could download the information. Some of the new ones can download it on the aircraft itself, or physically take the chip out and put it into a special separate machine. Okay, so there's quite a few bits and pieces there. Example I've got is engine like the G90. Engine has been using that electronic debris monitoring system, separates the particles and air from the oil, and uses a magnetic inductive particle sensor that will analyse the number and size of the particles to give you a more accurate assessment. Basically, we wash this in petroleum ether, so it's like a white spirit, because petroleum ether isn't oily. It cleans all the oil off. Then we put this debris on this little carbon sticky tack. Okay, but some aircraft do it automatically. Okay, so that's the DMS system. Good oil filters, yeah, another line of defence. Of course, oil filters, scavenge filters, whatever it is. Again, that can give an indication what's particularly or potentially going wrong with the engine as well. Again, we take these out, don't just take them out, put them in the bag and send away. You will have information on it where the aircraft tail number, the flying hours, maybe the engine hours as well, time and date if you did it. Again, have a quick look yourself. Although you might not go and test this, you're the first line of saying, oh, that looks okay, that looks normal. You will recognise the experience what looks normal. But if you find something that shouldn't be there, like, ooh, what's that red part there? That's not normal. Then go and highlight it immediately. That'll get priority to be tested and probably checked out just in case there's something not quite right. The main part is the oil filters prevent any debris or foreign matter from going around, because maybe a self-lubricating system, you don't want the oil being contaminated, so that'll be first line of defence. The spectrometric oil analysis program. Modern engines, gearbox contain a number of metallic elements, and the most common being iron. So obviously metal made of iron. Okay, copper and aluminium, magnesium, tin, silver as well, and also good old nickel. Okay, so all these types of materials, if you put it through a spectrometric oil analysis program, what a lot of it involves is actually going away to a specialist company, usually Kinetic, where they'll actually burn the oil and any of these components in there, if they burn, they will release a certain amount of energy in a wavelength of light. And what the spectrometer analysis program does, it analyzes that wavelength of light. And that way we know that a wavelength of light, when it's burnt for copper or tin, will be specific to that type of material. So by finding the wavelength associated with each of these materials or components, that can tell you, right, okay, you've got high concentration of magnesium, or where do you find magnesium in the engine? Oh, it's that part there. So you can actually diagnose a fault within the oil system, that a certain part of the engine is breaking down where it shouldn't be. Tin, silver, nickel, yeah, that can be part of a bearing. All right, so we have to watch out for that as well. So it's a very precise method of diagnosing. Again, just by looking at an oil sample, you can't tell it. However, you guys can initially, if you can, I don't go drinking it obviously, you can smell oil. Oil when it's used will smell a certain way. If it's been overheated or it's been contaminated, just do a quick sniff check, go, oh, that doesn't smell normal, go and get analysed. If you suspect any oil contamination, get it analysed as quick as possible. Okay, don't let the aircraft fly until it has been analysed. Okay, it might just be nothing at all, but again, it could be a lot of problems. Maybe the wrong oil has been put in there. Maybe someone's put hydraulic oil instead of normal engine oil by mistake. It can happen, even though there's certain ways of preventing that. It still happens to this day. Some people put the wrong tin on, and they put the wrong oil in the wrong engine. And likewise, gearbox oil, hydraulic oil into engine oil, and engine oil into gearbox oil. You know, it can cause a lot of problems. Okay, again, specialist ways of health monitoring. Vibration monitoring we looked at yesterday. Yeah, so there we've got our normal cutoff point, that red line here. That would be a normal, the maximum amount of vibration allowed in an engine, what we call a pass-off. Okay, and in this case we found a pass-off test for a fuel pump would be 2.5 that we saw yesterday, but as we saw yesterday, it reached 10.5, so the fuel pump's definitely on its way out. Also mentioned that if you get spikes, now depending on what the frequency is, this could be interference of something else, or it could be another component. As you can see, this one's very, very close to the maximum limit. Well, in theory, that's allowed to pass off an engine, but in good practices on a test bed, we could find out what that vibration is from. It could be the fact because it's a brand new engine, it's bedding in. We might do another one. We might just get the engine to bed in. But if we found that, let's say that was a centrifugal breather, because that's so close to the maximum line there, we'd probably go and replace that centrifugal breather to get the vibration back down to a more acceptable limit. Because that's almost at the maximum limit, well, the longer that engine runs, a good chance that's going to get worse. So you could go and fit this engine, and within maybe 10, 20 hours, 50 hours, that would be out of limits. So you have to take the engine out. So there's no point sending an engine out very close to the maximum limit, where if you can fix it before you give to the aircraft, that make it a lot easier. Again, that comes down to experience as well. But obviously, you can see here, yeah, the fuel pump's gone way, way above what it should have done. Okay, but normally it'd be round about the green line here. Okay, and you can see harmonics of it going through. All right. So vibration, again, that's real time. You can see this vibration on screen real time actually is happening, and you can print out real time as well. And that's called a pass-off test. What I'll try and get for next one is called a waterfall one as well. Obviously, engines, you can fit as many transducers as you want as required. Usually one for front, one for rear. That's pretty much the standard, but you might put an extra one on the side. Obviously, you get a warning light in the control panel when the vibration limit has been exceeded. It's important that the vibration sensors are not loose, because that can give a false information. And likewise, when you fit them, make sure you use the correct torque setting. Over torquing them can put too much pressure on the sensor itself, and that also can give false indications. So example of the vibration trace got there. Again, the green line shows the pass off, the red line the maximum allowed. And that's a typical sort of vibration you will get. Your aircraft integrated data system, or AIDS for short, again, monitoring certain parts, engine parameters, either manually or automatically. We can't detect failure before it happens. So it's analysing real-time information before it gets to a point. It'll have selected engine performance parameters and record for analysis and fault detection. Also, it'll go back to your ADR as well, which is recording magnetic tape. So after each flight, magnetic tape is processed by the computer and the results are analysed. If they find any sort of parts that are way away from the normal or the reference data, it'll enable the fault identification and action taken. So magnetic tapes, again, that's old school as we call it. They tend to move on to some systems now can interlink with manufacturers and engineers, whilst the aircraft is actually flying in real time. And certainly some of the modern aircraft I'm working on, and even commercial aircraft, they literally fly over the airport, they download information as it's happening, download to the computer in the airport, and that will start printing out job cards. It'll actually tell you what is wrong with the aircraft before you actually download anything. Some of the new multi-jets we've got, they do that as well. So it's hardly any going plugging in now. We might have to plug in just to double check something, but certainly the aircraft will download all information. Computers on the ground will also do some real-time analysis, and eventually that can give you some idea of what's going on, what needs to be fixed or looked at. So engineers give some real time. And you'll see that as well in Formula One racing. Formula One racing, they're getting telemetry back to the engineers in the pits, so they can tweak the engine as it's driving. They can actually increase or decrease the parameters on the engine capabilities as the engine is actually going around the racetrack. And likewise, not so much with aircraft, they would wait till on the ground. You don't want to adjust anything in the air, because if it goes wrong, then it's going to have a lot of people on board. But certainly Formula One uses a similar sort of system, so they can tell the driver what to do, and if it comes to the pits, they can do certain tweaks. All done by computer, the joys of technology. All good stuff. So trend monitoring, again, that's a mixture of everything. All parameters are measured using engine health monitoring systems, as we've just shown you, and can be recorded. And that means by monitoring it, we can see through time how an engine is actually getting on. Okay, the one there, it's not the best diagram. Oil pressure ratio at sea level, and you can see through the years how it's been working on various parts. Not the best diagram. I might change that one out actually. But it's a trend, it's a graph. Every time you fill oil in an engine, you'll mark it in the book. Well, it might be in the computer now, obviously, but set in the book, and you can actually plot the oil levels in the actual physical book. 700 we still for the aircraft. We'd maybe put 1.5 litres of oil in. Next day, be 1 litre, 1 litre, 1.5, maybe 2, 2.5, 3. So you actually join the dots, and you see a line starting to go up the way. So we start to use oil. Why are we using oil? Is there a labyrinth seal breaking down? Again, magnetic chips might be able to help you diagnose that. So if we start to see a trend where something's going up or getting out of limits, we can leave the engine as long as possible, providing that trend line is staying nice and average. If it starts seeing a sharp spike, then that's when we can do preventive maintenance by possibly removing the engine out. What I've got coming next, I've got to show you an example. This is a system I used to use on the 19 engines on the Tornado aircraft. It used to be an AFDC. It gives you an example of trend monitoring. Okay, and this is it's not in your book. It's just an example of what we had. This was what we call RIPS, RB19 installed performance software. We'd have all the data of all the aircraft, all the engines fit to the aircraft, and we'd have all the parameters of those engines. Okay. So like today we'd have a traffic light system for normal, caution, and alert, and reported. In other words, once we put all the information in about the aircraft, once we tested the magnetic chips, any other parts, we could, computer will analyze it all, and it will put the aircraft into one of these categories. So normal, yeah, the engines are fine. The L and R means left engine, right engine, it's twin engine aircraft. The ZE numbers, that's the tail number of the aircraft. But as the trend is starting to get higher, maybe the oil level is getting higher or the vibrations getting higher, it will start to put to a higher alert. Alert is where we have to have a look at. So every time you open the computer up, some aircraft being alert, we go and analyze it and then tell the engineers to go and look at that jet. If it's been reported, then something has also had to be carried out on. So some information we would get is a screen like this. We've got NH, so your high pressure spool and your low pressure spool. This engine actually had 3 spools, intermediate, but we didn't bother looking at intermediate. We were more concerned with your NH and your NL. And to show some information, there's the engine number. There's the aircraft flying hours, so 1,900 odd hours. Was ECS on or off? Because if ECS is on, you're taking air away from the engine, so that can affect thrust patterns and that sort of thing. Aircraft number and the engine position. Okay, in this case that would be right-hand engine, and it was on the F3 aircraft, date and time, back in 1996. Some of you probably weren't born. All right, so we've got NH, we're looking here where it should be, green line, but it's starting to go down. So the performance of this engine was starting to go down. So at this point here, we actually replaced the engine, all right? And there's a new parameter started there. NL wasn't too bad, but it's starting getting higher. You know, it was going out of TBT was turbine blade temperature. Instead of EGT, we had TBT, turbine blade temperature. So that's a nice sort of line you want there, but all of a sudden, in conjunction with that part, it's going up and down, up and down, up and down, up and down. Now we can, in the computer itself, we can move these lines across to specific points, and the computer will give a general recommendation. Again, to be honest, it comes more down to a set procedure, but it can give a recommendation. So there we go, there, moving the line across, I can check certain points in that graph. And there we go, it comes up with compressor dirty damage or turbine damage, because the performance of the engine was going down, NH spool was getting worse. Well, if NH spool is getting worse, then NL gets affected as well. Okay, and get to a point, we've got an alert there. Green's good, yellow's not as good, and red's certainly not very good at all. The temperature was averaging out not too bad, it was going up and down a little bit here. So again, we go and get a performance run on that, find out what's going on, and then possibly reject the engine. So there we go. We'll check there, we found out what was going on with the aircraft. Okay, so see with different engine numbers there. So we've got engine was changed at this point, but 7132. Then look at this, a different example. Again, compressor dirty damaged, trend's going up again. And again, a different engine. We're looking at point here. ECU placarded. So in other words, we've done the performance run. There'll be numbers in the book of what the engine should be. We'll do a real-time run. We'll take the numbers from the gauges, what the gauges read, we'll make a note of those. We'll put them into the computer system. It will do a calculation, and what it will do is give us something what's coming up now. So this would be after we've done an installation run. It could be a pre-dirt check or an installation run. So again, you've got the aircraft number, how many flying hours the engine's done, the engine number itself, the position of the engine, and the mark, the type of engine. Okay. You've got what's called SOT rating, or thrust rating, depending on the engine, NH speed, NL speed, and these numbers are from the logbook. These are what the numbers should be. All right. These are the numbers we've taken from the actual ground run, the real-time run. Okay, and that's the numbers we observed during the run. So for NH was 96%, NL was 95%. Line 1, line 2, that would be like FADEC A and FADEC B, just we had a different system on this aircraft, but it's pretty much the same scenario. Fuel flow, 37, outside air temperature, 15, 800, 800. Now, because we put the temperature in and whatever, it's given us an alert. It's told us that NH is not quite what it should be. It's a bit lower than what it should be. There's NH there, yeah. On lane 1, now that could be a DECU fault, a FADEC fault, it could be an engine fault. Again, we would download this information and go back to a trend graph and see what's been happening with the engine, so we can help find out. So we'd have to go and check that. We go and maybe do a ground run again, recheck the figures, and then if required, what's coming out here, it's told us that NH is outside limits. So it's allowed a percentage, that's what it should be. These are the figures would be from a test bed where the engine has been in a cage, tested, and then delivered to the aircraft. But for some reason, this run, the NH spool has gotten lower. Now you also notice that, look at NL, NL is also slightly lower, so both spools have decreased slightly. It could be something simple, it could be needing a compressor wash or something like that. Everything else though was okay. TVT was okay, and that was the results there. But it's just outside the window, and every aircraft will have some sort of system like this to analyse. You're going to do a ground run, you'll get your information, put it in the computer, and it will tell you basically yes or no. Anything comes in red, it needs to be looked at. Anything green is good to go. Now I mentioned the log car again. This is an example. This is taken from our military ones. Again, this is the information that you would get from the test bed. Okay, so you have your ground run date, your lane ones, your NHs, your NLs, your ISA, and any modifications that have been carried out in the engine. That can affect the information as well. Okay, this side here, this square here, that is from the ground run that was carried out in the test bed before it was fitted to the aircraft. So there's your figures, your 98, your 97. That's where it was passed off, all within vibration limit. The amount of thrust, in this case, there's a good engine, this one, 39 kilonewtons of thrust. So you've got a good thrusting engine. So then once we put our engine ground run data in, which we'd actually carried out, okay, all the information in, and then what it would tell us, you know, as I've said, we've got a deck in the aircraft, you'd have a FADEC, but that would tell the potentiometers in that decu, we could change to make sure that's the figures. We plugged in the test equipment, these are the figures that should come up. So say, for example, this pot here, a potentiometer pot, was reading 7.96. This is what it should be. We'd dial that indicator to read 7.98. Now remember, if you adjust any conditions on your FADEC, for us it was a decu, you'd have to do another ground run, confirm it was working okay. So that engine we just saw before, where the NH was slightly down, it might be a case that one of these pots was maybe not correctly dialed in, or it was out of limits. So we go and adjust it to match the figure that should be in the book. Okay. So this is an example, and this would be signed off like somebody like myself once we've done the ground run. So again, just to give you an example of what you might come across. Commercial aircraft will have something similar, just a slightly different version. Okay. So just to give an idea of sort of real time what we used to work on. Now, trend monitoring, vibration, again, things will wear out. You will always have vibration. There's a permissible and maximum amount of vibration allowed on every aircraft. Bigger the aircraft, the bigger the chance of vibration. As the aircraft's trundling down, you'll all be in an aircraft, I'm sure, at some point, flying down the runway, you hear squeaks and bumps and grinds and groans, all rumbling down the aircraft. Some aircraft are more rough than others. They can be transmitted through the fuselage, and the pickup points on the engine can pick up that. So there are aircraft limits and there are engine vibration limits. So again, when an engine is in a test bed, it will be a certain amount of vibration is allowed. Once it's fit to the aircraft, it will be probably increased a little bit more. So max permission vibration, for example, may be as follows. So when you fit an engine, nice new engine, at installation, you might be allowed 25 microns. During normal operation, it'll go up to maybe 50 microns. And with a single increase of maybe 20 microns, so a spike in effect. Now, vibration is an indicator of the wear and amplitude. All right. Frequency of vibration indicator of the components vibrating. Of course, the value is monitored and recorded as amplitude. Okay, so in the flight deck, a meter that will indicate the overall vibration experienced by the engine in terms of amplitude. In other words, how much vibration have we got? Most maintenance manuals will give a conversion for this into mils or microns or inches per second. It depends on the type. The tolerance available is not necessarily that straightforward. Basically, if it hits an indicator in the cockpit, you need to go and check and do a vibration run on the engine. And there's some sort of typical setups. There's the airframe hours, okay, along the bottom, and the actual vibration amount. Okay, the trend line, so hopefully it's on that or below. So green is good, you're allowed a certain maximum installation, and then standard, but then you get natural wear and tear. So eventually it will start going past the maximum amount. But again, you might have a point where a spike, vibration is exceeded. That could be a heavy landing, that surge, that sort of thing, that can cause it as well. So inevitably, through time, engine will degrade, vibration will increase, and then the rise is called a trend line. Sudden increase, amplitude will be noticed immediately by what we call excursion. Just as it could be anything from a bit of debris, it could be heavy landing, lots of things. But if you do get one of these spikes, you're going to have to do something about it. You're going to have to go investigate. So again, plug the vibration equipment, do a test run, and there's various methods of doing it. You can do the instant vibration, like the vibration trace we show with all the spikes, or I must try and get a photograph of one, is what's called the waterfall vibration, where you take the throttle up. In our case, it's about 2.5 minutes. So it took you 2.5 minutes to move the throttle from idle to maximum. So you imagine your hand at the end of that time is quite sore, but it's a very, very slow, continuous movement of the throttle all the way up to maximum. It would take 2.5 minutes. You let it settle, and then you bring it back down 2.5 minutes. Okay, again, every engine will be different. And what you got, it looks like a mountain. All right, hence we called it a waterfall. There's reds, yellows, and blues and whites. The more intensity to the vibration, the whiter the colour. So dark colours are okay, but the whiter or redder the colour, the more intense vibration. You always get specific vibrations at certain throttles. So you've got this mountain-like effect. Instead of having the vibration instantly, it was a waterfall effect. And that could give an indication exactly, in conjunction with a normal vibration trace, a bit more in-depth diagnostics of any potential vibrations. Plus, you would feel it through experience, not so much maybe the bigger aircraft, although you will feel it depends on the position of the engine. Set in my aircraft, our engine is very close to us. We are literally sat between the engines in a fighter aircraft. So any vibration you would feel in the floor, you actually feel the floor start to vibrate. So you'd be looking at indication in the cockpit, you'd be checking with your colleagues outside, any indications of anything obvious, no, okay. Depending on experience, you go past it, and if the vibration kept on going, then obviously you bring it back. If it went away, you'd make a note of when it went away, okay? And then you bring back down to idle, let it settle, take it up and see if it happened again, okay? But again, always following the procedure. Don't deviate, just don't try something for the sake of trying it. You must always follow procedures. Okay, so again, there's a typical sort of trend line. All right. Okay, doke. Vibration monitor, covered that one. Is trace micron. So yeah, those numbers I mentioned before, the microns, maybe worth making a note of those in the book. Okay. And what we'll do, we'll just do a quick finish on the oil, and then we'll go for another break. So again, you've got oil, you've got the vibration monitoring, you've got oil monitoring, you've got temperature monitoring, vibration, all the good stuff, and also you're checking your oil monitoring system. Again, the same way as the rise in vibration amplitude can be recorded via a graph, so can several factors involved in the oil system. Okay. So we can be looking at things like consumption. Is the engine using more oil? Like I said, you'll plot in the graph on your engine book. Once you've done a service on the aircraft, you'll mark how much oil you put in for that day or that flight. Debris from your chip detectors, debris from your filters, your strainers, any results from your soap samples, etc. There may be other solid systems and indications. Again, not really recordable, but I will observe through experience. Again, like I was saying about smell, you might be taking a pipe off or checking something. You go, oh, that doesn't smell right. I've said before. The soap samples give a really good record of contaminants. If you suspect any contamination of oil, go and get it sampled. Okay. Again, that'll be checked for any problems there. Any graphs, again, we can keep engine as long as possible. We don't mind wear and tear, but provided it's within limits. Yes, we know things will wear out through time. Everyone gets older, wears out, just like myself. Okay, so we can keep an eye on the graphs, whether it's the vibration, whatever. You can keep an eye on all that. All right, not a problem. Okay, so yeah, all that good stuff, it can lead to more efficient and safer interpretation or inception of faults and defects. So again, a good old engine there. Right, so we've got oil temperature sensors, fuel heaters, exchangers, etc. And we can have actually a gauge on there. Single gear engine cases can actually have oil indication on them. We never had the joy of those in the aircraft I worked on, but some of the new engines will have a capacity to actually show you levels of oil. And again, if the oil level gets too low, you have a warning light come on, just like in your car, for oil pressure. Okay, so your basic oil system. Pressure sensors, yeah, low oil pressure sensor, again, and then obviously you've got scavenge pumps, filters, chips, and all that sort of good stuff. And again, you might get an indication that the oil filter has been bypassed. Well, we need to know that. Why is it bypassed? Has there been a blockage? Is it the type of oil? Has it got too hot? Again, all these sensors will interact and give the pilot and indeed yourself as an engineer a warning in the cockpit. Okay, so the more sensors, the more information we can have, the more lights that can flash at you in a cockpit and give you a warning. All right, but preventative maintenance better than cure. If you get any faults, you try and rectify them where possible without removing the engine. You try and keep the engine in the aircraft as long as possible. One, it keeps the aircraft flying, and two, it keeps the cost down to minimum. Any time an aircraft's on the ground because of a fault, that's costing the airlines lots and lots of money. So again, it's all about cost. But the main thing, it doesn't matter how long it's on the ground for. Yes, it might cost money, but at the end of the day, safety comes first. So never cut corners, never say, oh, that'll do for the moment. We'll fix it when it lands next time. No, if it needs fixed, it must be fixed. You've got people's lives in hand. So look after your tools, look after the aircraft, look after the engines. They'll look after you and keep everybody safe. That's the main thing. As I keep saying it, metal can be replaced, but you can't be. Okay. Okay, I think we'll go for another break and then we'll look at engine performance after then. We'll maybe do a bit of recap first, actually, after that. So go.
Engine run.
Yeah, when would you carry an engine run?
Oh, I mean, when we change the engine.
Yeah. Yeah, change the engine. Yeah, all's good.
Yeah, when we do maintenance.
Yeah.
Of certain part which affect the performance of the engine.
Yeah, good.
Then sometime we do have a schedule engine run, right?
Yeah, you're doing the health one, like I showed you that example of RIPS. You're checking the performance of the engine. Even though the engine's working fine, after so many hours, you must go and check how the engine's doing. Even though it's working fine, I've done one where we went into an aircraft, there was no faults with the engine. It's called what's called a periodically. So in other words, periodically you go and check the engine.
Periodic,
yeah.
Yes.
And he's supposed to borescope the engine first. We thought, well, it's fine. We'll go and run the engine first. Run the engine. Engine's great. All the indications are normal. We let the engine cool down. Then we borescoped the engine, and we had guards on. Everything was done correctly, and we found there was damage to the turbine. But the turbine was actually still working properly. It was still giving the amount of thrust. But it was damaged, and the damage was out of limits. So although the engine was working properly, because we found the damage, we had to reject the engine, which was a pain because it was working fine. There was damage to it. So things can be damaged, yet still working. But because that was called through for the periodic, with to reject the engine, it was a bit of a pain. But these things happen. Yeah, good. So yeah, McCall to do for. You might want to check another part of the system, of the aircraft system, hydraulics, electrics. You might want to put power on without using a ground power unit. Depends where you are. You might not have that facility available, like a hydraulic power rig. So you might have to actually start an engine up to check maybe things like cabin conditioning, ECS. So you're just using the engine as a generator, okay? So you're not testing the engine, just using it as a power source, in effect, yeah. What sort of information might you require for an engine run?
Elevate temperature.
Yeah.
Yeah, outside the temperature, yeah. Well,
Wind direction.
say again? So I missed that last one. What was the last one?
Wind direction.
Yeah, shade temperature. What else?
Ambient condition.
Ambient conditions, yeah. Usually you get in touch with air traffic control because they can give you the temperature, the pressure, weather conditions of the day. You know, you might be going to do quite a long ground run. It might be a brand new engine you've put in, so it's going to take an hour or so, maybe do the tests and adjustments, because not all engine runs go straight away, as in you might go and test an engine, it's fine. Some engines you go and test, and you might have to go and do a few adjustments. Yeah, you might have a leak, you might have an adjustment on the FADEC or whatever. So you can be there for a while. You can be there for maybe a morning or an afternoon. So it's worth checking with air traffic control to find what's happening with the pressure, temperature, and also the weather conditions, like wind direction, and are the conditions going to get worse in the afternoon? Can we get all the ground run down, or is it a case of going to have to wait maybe till tomorrow? But again, it all depends on, like I said before, the longer an aircraft's on the ground, the more money it's costing the company. So they want to try and get the job done as quick as possible, but obviously safely. There's no point in taking the aircraft out to minus 50 degrees and there's howling winds. Yeah, it's not good for anything, you know. So again, try and do it sensibly as well. Okay, safety precautions. What other safety precautions would you? There's loads of safety precautions. What would you want?
A lot. First of all, we have to follow the instructions.
Yep.
Then we have to watch out for the FOD.
Yeah, FOD, yeah.
Wind direction.
Yeah.
And danger to personnel.
Definitely, yeah. You want to inform not just the people you're working with, but any other trades or any contracts could be on about. But usually on an airfield, you'll have a specified zone for ground running, which is a nice, safe environment. But there could be things like people in the background, bird scarers, you know, going in their cars. Contractors could be in the airfield working. So again, safety first. Make sure there's nobody behind. There's no equipment behind it. So yeah, what about the physical positioning of the aircraft and how it's fitted or positioned in the designated zone?
The line path?
Yeah, it should be lined up properly and obviously into wind. How about the wheels?
Wheels should be chalked on.
Yeah, chalk, but it depends on the run. If just an idle run, you can get away with normal chalks. If you're doing high performance runs,
yeah, then we have concrete, concrete chalks.
Yeah, concrete and usually specified special chalks, so usually big metal ones that get bolted in position. It does depend on the aircraft and where it's getting done, yeah. What else? What else do you think? You're going to start a big bit of metal. If it's very cold, it's going to get very hot quickly. So there's a chance of what happening?
Chance of fire.
Yeah, fire. So what might you need?
We need to avoid such condition.
Yeah. So if you've got a brand new engine, what's also advisory getting to be very close to you? Most companies should do this. If they don't, I'd be very surprised. I usually get the fire extinguisher. The fire section usually come out for a brand new engine run, as we call it fire cover. Because it's a brand new engine, it's not bedded in, you've just connected it, just in case something goes wrong. Not your fault, just one of the mechanical things. At least if the fire section are there, once you've got the engine running, everyone's happy, then you can wave them away. It's just for the initial startup, the very first start of a new engine. It's always worth getting the fire section out for a new one. Okay, but yeah, fire extinguishers. You'll have fire extinguishers beside the aircraft. So you have people in the cockpit operating the engine, supervisor outside, safety person or persons, depending on there for the APU, the engine start. So fire extinguishers available as well. Ground running guards to cover the intakes to prevent FOD that you mentioned already. And what about yourself? What should you always make sure you're wearing?
Ear protection.
Yeah, definitely. Don't think, I'll be okay. Yeah, as you get older, your hearing gets less through natural age. It can get a lot worse with constant being surrounded by noisy aircraft. So make sure you look after the ears as well. Okay, there's a bit in the book. We give a bit about ear noise protection. It shows you prolonged exposure to noise within a certain distance and certain areas where ear protection must be shown. And on one of the pages, it gives you noise decibels at certain meters. So again, short exposure to high noise is okay because ears will recover. But if you're exposed to lots of long, high duration noise for a long time, especially on high performance runs, that can affect your hearing. So always make sure you have ear defenders. Vibration as well. We used to wear, we stopped doing it, we used to wear kidney belts because we used to have a reheat on an engine, which is a very rumbly engine. It would actually shake your kidneys to bits. So part of precaution, you used to wear a safety belt to help protect the vibration of actually shaking your internals to bits and pieces. Okay. All right. Yeah, but the main thing, keep into wind, forward protection, safety personnel, any equipment that shouldn't be there out of the way, etc. Good. So you're just about to do the ground run. You've set the aircraft up on the ground dispersal area. So some of the preparation for ground run, what you're going to do. You've mentioned checklist. You've got a checklist. So what else would you do?
You have to remove the covers.
Yeah, all the blanks. Yeah.
Yeah.
So that'd be a bit of
blanks.
Yeah. And then fit the guards, intake guards as well. Before you fit an intake guard, look inside the intake guard. Sometimes people just put a guard back on the shelf or back in a trolley, but they can be sat outside sometimes, and birds or whatever, insects can be in there, and even debris can get blown into the guard. So when you put the guard on the engine, then the engine will suck the debris that's in the engine. We had that once where the brand new running guard, it was all painted, all nice and fresh. We took it off, put it on, and what had happened, another guy, it was a bolt had been left in the, or a rivet, I think it was a rivet actually, a rivet had come out, sat in the bottom of the guard, and they gone to the spray shop and they sprayed the guard and also sprayed over the loose rivet. So the loose rivet had stuck with the paint to inside the guard. So when the person picked it up, they shook it, yeah, nothing there, because the loose rivet was stuck by paint. But of course, when it went onto the engine started up, sucked the rivet off, straight into the compressor blade. That was just the compressor blade that was damaged. There's no other damage. Caused a bit of vibration, but unfortunately, that meant the engine they just fitted, the engine had to come out. Okay, so it was an engine replacement, unfortunately, because you can't, on that engine, that specific type, you couldn't take the compressor blade out on its own. So it had to mean that the engine had to come out, and then the whole compressor module on its own would have to be replaced and then get stripped down. So it's a bit annoying when you fit an engine and something simple as that has broken the engine when it shouldn't have done. But it wasn't the person's fault. He checked inside, but because it was all painted, you couldn't see it. It was only until enough suction of the engine sucked it in. So yeah, just be careful. Don't take things for granted. Make sure you don't just grab a tool or an intake and just put it on. Make sure it is clean inside. Give it a quick shake. Make sure there's nothing inside. Good. Okay, what else might you do or need?
Not in Nepal, but for you, you have to check IGVs.
Yeah, make sure for icing, that sort of thing, yeah.
Then check oil trends.
Oil levels, yeah, for gearbox, CSDUs, IDGs, whatever else.
Starters.
Yeah. So you're going to start engine. What do you want to make sure are closed? So you're going to have a lot of engine power. What do you want to make sure everything's, well, you want to sure basically all the cowling, the doors are closed that do not need to be open. Yeah. You might leave the cowlings, the sea ducts open for idle. You might start the engine at idle and then do a dynamic leak check. Sometimes they do the door shut, depends on the engine. Some engines we'd start with the door up, provided your intake guards are on, because you only go to idle to do a certain check or adjustment. You might have test equipment fitted, which means you have to have the door open. Okay, but you wouldn't do high performance runs with test equipment fitted. Yeah, we didn't do that in the military. We'd have the test equipment fitted. The only one we would have with high power settings was a vibration run, and we'd be inside a shelter, special shelter. We'd have the test equipment inside the booth, the big long lead behind the intake, secured, and because we had to do a full performance vibration check, this 2.5 minutes up and 2.5 minutes down. So sometimes you do have to have certain panels open, but they must be secured so they're not flapping about in the wind. So again, it's all common sense stuff. Make sure nothing's loose. Safety as well. Again, the clothing, make sure you're not wearing loose clothing just in case you get close to something. Your high visibility jacket might get sucked in, that could draw you in. Don't go too close to an intake. So safety, safety, safety. There's never enough safety. It's very easy to forget exactly what you're working with, and next thing you're getting injured. Okay. And also when you're moving about the aircraft, because you've got an engine running, that means you've got hydraulic power. Okay, so if somebody's in the cockpit and they move and they've got their knee close to the joystick or the control column, that can move an aileron. Or, they might have moved a system might have been activated with electrical power, but it won't work until hydraulic powers. So be very careful with switching the cockpit. You'll do a pre-start switch check to make sure everything's off bar certain switches. If somebody's maybe activated a flap control, left it down as they switched hydraulic power off before it's moved, next time you apply hydraulic power, it will move. Flaps will move, your ailerons will move. And some aircraft, like our aircraft, the military ones, the wings would move, or air brakes and things like that. So again, always be very careful when starting things up. Okay, good. Again, the following sheets will give examples. Just run through some basics. Most of it was obviously common sense stuff. Things like, do not try to stop a fan blade with your hand. Yeah, it's going to hurt your hand. Make sure landing gear, sound, ground safety is in chock. Yeah, I've done all that. Do not run an engine with thrust reverse cowls open, because that's going to cause problems. Again, if you are activating thrust reverse, make sure there's nothing in front of the engine that can potentially go back, and then even with the debris guards, maybe damage the debris guards. Other bits and pieces. The only ones I really highlight from those pages are things like safety distances. They give example there. For an engine ground run, make sure no obstacle nearer than 50 meters in front of it, or 164 foot behind it. But that's just an example. The safety distances will be specific to every aircraft. Some will be longer, some will be slightly shorter, maybe smaller aircraft, but in general, gives you some good ones. Always figure out the wind limitations as well, and we do have an example in the book there to show you. But again, it is a table, it is an example. You won't be asked shouldn't be asked a question on that because it's more type specific. But one of the big ones is with FADEC especially. They might ask you a question on FADEC. What would happen if you have an engine which shuts down uncommanded? In other words, it shuts down its own. What's the first thing you would do? Dick and Jenna?
Yeah.
What would be the first thing you do if an engine shuts down on its own? You've not shut the engine down; it's shut itself down. What would be the first thing you do before you can check anything?
Switch off the engine because it may start automatically.
Yeah, that's right. So you've got an engine master switch to the cockpit. Switch that off, because if you don't, you leave power to that FADEC, and the FADEC might go, "Oh, I'm okay now. Let's go for start." And you've gone, go and check the engine. Next thing, it started up itself. Okay, so make sure power is off. Good. You might find some procedures that if you have a fault like that, yes, you switch the power off, but it might also suggest that you trip the circuit breakers, just in case. There's maybe a fault with the FADEC itself. It might have a short circuit somewhere. Again, as precaution, just make sure there's no power available to that engine. Well, it depends on what the situation was as well. Okay. It says there as well, if you only change the position of the engine mode set from engine start to normal, the FADEC system will complete the abort, but there is a risk of the engine will start on its own. Again, and that can cause severe injury or death, so just be very careful. Monitor start cycle carefully when the air started and the pressure is lower than the recommended pressure for operation conditions. Can cause problems, can cause high GT. All right. With engine handling, to make sure you've got accurate readings on your gauges. Let's say you're doing a performance check. You want to check the maximum figures, your EGT, your RPM, each spool speed, and that. What would you make sure has been switched off? To make sure you've got the correct readings for your real-time readings that don't affect.
We have to check the fuel system adjustment and ensure all the air intake are off.
That's the main one. Yeah, the air, any air off takes, and for cabin conditioning, anti-icing, pressurization, all that sort is all switched off initially. Because if you switch those on, you're taking air from the engine, so that will give you a false maximum reading, certainly at performance on. Yes, it might work okay, but you want to check the engine before you switch any loads on. Okay, that sort of stuff. What would you do if there was a sudden increase in TGT or AGT, any unusual noise in the engine? If you're doing an engine run, what would you do?
We have to stop the engine.
Yeah.
And like carry out the investigation.
That's right, yeah. Anything that's not normal isn't normal. So we need to shut the engine down or at least come back to idle. Depends on the situation. Yes, you might get vibration. Say you got vibration around maybe 85, 90% RPM. You don't necessarily have to shut the engine down because as you bring the throttle back, if the vibration goes away, well, okay, we can try and figure out where that's coming from. We'll do a vibration trace. But if it doesn't go away as you bring the throttle down, then yeah, we need to shut it down quite quickly. So again, it depends on the situation, how extreme it is. Was it a one-off, or is it, is it fuel flow? Is it lots of things? So again, you let engine stabilize. If you've been at high power on, come back to idle, let stabilize for 2 or 3 minutes, and then slowly go back up until you get to that point of vibration again. Make a note of it, and then depending on experience of what's going on, you can either go past it to see if it goes away or find it comes back. But again, it depends on the actual situation. You don't always have to go past it. Sometimes there should be vibration at that point anyway. Come back down, shut it down, and do a visual and internal check as required. Again, you just follow the manual. You will get experience. You'll start to learn. Yeah, we're going to have to do this. You'll know off by heart. But maintenance procedures do change, so make sure you keep up to date with any changes that happen. In old days, we had books, and to change a book would take weeks, sometimes months to change. So something might have been changed, and you'd be following the manual, but it actually was changed 3 weeks ago. But by the time it came to get printed, it'd been 3 weeks out of date, so it was already out of date. Nowadays, books are not used, or manuals are not used. The manuals are on the computer because they can be updated straight away. Okay, if you print anything out for a quick guide, that is already out of date. All right. So always make sure when you sign up any job, any task in accordance with manual AP 123 paragraph 4, whatever it is, again, it's all with the one on the computer. Okay, so give me examples of a typical checklist for an engine ground run. So you do an engine run, you start the engine, give me some typical checks.
Check of idle RPM.
Idle RPM, yeah.
Yeah, record all the instrument reading.
Yeah.
And should be make sure that low pressure warning light are out.
Yeah. What other pressure lights should be out? What other pressure lights should come out? Go out. So your fuel lights should be out. Your fuel flow going on. What's one of the essential ones you don't want to see on? Reference pressure. Should go out quite quick as you start an engine up.
EGT?
Not EGT, yeah, because that's constant. You'll have an EGT gauge, but what pressure light should go out quite quick on startup? Think about LP2. That gives you a clue.
Low pressure light.
Yeah, the oil pressure light should go out once it gets to sort of 55, well, 4 psi and all that sort of stuff. Just like your car, yeah. Yeah, so what other checks might your car out with engine when it's running?
We have to check the throttle range, full range of the throttle.
Yeah, full range of throttle, so idle to maximum. So we'll check full range of that. And you might do acceleration. So you'll put the throttle steadily but quite quickly, and you'll check how fast or how much time it takes to go from idle to maximum. And then you'll do a deceleration one, do the opposite. Let's stabilize at maximum, then rapidly bring the throttle back to idle, and then again time, so how long it takes to go back to idle. So we've got accel checks and decel checks, as we call them. What about thrust reverse?
Reconnect the thrust reversal.
Yeah, because in there it's a bit of a weird one. When I first saw this in the FADEC, I was like, okay, that's different. Normally for On my jet I worked on, you wouldn't disconnect it because the throttles were slightly different. You just rocked the throttle to the side. On commercial aircraft, slightly different. To say disconnect it, check the range, check the movement of the actual levers, you get full maximum. But again, I would check that. I mean, follow procedure obviously, and make more common sense to check it before you start the engine that the actual movement of the lever is proper. Then it says you to reconnect the engine once you've shut down the engine, reconnect the thrust reverse, and then carry out normal thrust reverse. Yeah. There's another section we'll look at later on called power augmentation. So yeah, if you've got any water injection system, which is power augmentation systems, you would check for that as well. Again, when you stop the engine, what else would you do as you shut down the HP cock? What would you check as you shut the engine down? So you switch the engine off. Is that it, or do you check something? You can actually, the people outside can visually see this and hear it as well, because sometimes it can give you a noise. Just the rundown time of the engine, as you switch the engine off, person outside should be watching the engine. It's rotating and getting slower and slower and slower and slower. And also listen to the engine. It should sound normal. You'll become aware of the sound of an engine that shuts down. If you're shutting an engine down, it stops quite quick, it makes a funny noise, or something not normal, then yeah, that needs to be investigated. And different when it's got power behind it. When it's got no power, it should be a nice gradual stop, and then slowly tinkle, 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 and slow down, yeah? If it goes tinkle, bang, oh, that's not right, it makes a funny noise, then that needs to be investigated. All right, that's fine. With reference to FADEC engines, if you shut an engine down flight due to maybe a fault, if the engine has an inoperative oil system, in other words, it's not working, the windmilling must be restricted to how many hours?
6 hours.
Yeah, 6 hours. In other words, the air pushing the compressor around, you can do no more than 6 hours, because otherwise that'll just blow. The gearbox will spin and it will try and empty the oil because there's no air pressure behind it, so the oil will just escape out the bearings, out the lab seals, and you'll eventually have no oil in the system and potentially make the engine even worse. So if you've had to shut an engine down because of an oil system fault, then depending on how far out the aircraft is from landing, it's got roughly about 6 hours. But don't get me wrong, if an aircraft's flying over the Atlantic Ocean and it's in between somewhere, and it's got at least 7 hours to fly between the next airport, you've no more choice. It's just one of those things. But ideally, land within 6 hours if your oil system is not working. Okay, and likewise on the ground, you don't want an engine spinning because of high wind. So what you do, if it's the aircraft's down for a few days, blank up the intake, blank up the exhaust, not stop the engine rotating as well. Okay. Again, all these pages are pretty much more specific to FADEC. I think most of the questions, if I remember right, there's not much on these, but that maybe the windmilling one might come in certainly. And we'll keep an eye on that. Always follow the precautions about air inlets. Again, people positioned near the inlet during plant operation must be aware of the hazards of forward and beside it. Again, common sense prevails. If you've got an increase in wind, obviously increase the distance away from the engine, you don't want to be blowing into it. Again, things like wet surfaces, the ramp surfaces are wet or frozen, clean it, make sure it's suitable to walk on. Again, anywhere in dangerous areas, you just keep away from them unless you've got control in the cockpit and communications. Okay. Rightio, anything else you want to put in that one? No, that's pretty much it. Again, make sure you put your aircraft on a concrete surface, not like we saw in the photograph, the monoblock, because that's going to make a little mess. Okay, if you're shutting it down, it's worth waiting at least 30 seconds after the engine be shut down before you go in to do anything. Okay, because sometimes fuel drains off. Some aircraft will drain within a few seconds afterwards. It could be leaks on shutdown, back pressure. So it's always worth waiting about 30 seconds until you get a signal from the person in the cockpit, because in 30 seconds your engine will pretty much have stopped by that point. So he shuts the throttle down, and within 30 seconds, the person in the cockpit won't leave the cockpit until he's got all indications that the engine speed is at 0. In other words, there's no fuel flow, there's no ignition, and there's no rotation of the engine, or minimal rotation, where it's going so slow there's no chance of it starting up again. Okay. Once you get the indication or communication from the person in the cockpit, then you can go in and do what is required on the engine. Okay. Yep, that's good in there. That's all good. Again, those sheets are all common sense. Go and work ignition system after an engine run. Let it cool down. Open doors. Let it cool down. Wait your usual 1 minute. Disconnect power 1 minute or 3 minutes wear gap, etc. Be aware. Only note I've got is some aircraft do not have electronic centralized aircraft monitoring, which is called ECAM. It's more likely that the new aircraft will have glass cockpits. Now, what's mean by glass cockpits is that the indications are all on digital or LCD screens.
On digital, yeah.
Yeah, for your ICAS, so EICS, your engine indicating and crew alerting system. That tends to be the more modern now. The old versions were old analog gauges, or needles and gauges, physical needles, but nowadays it's all electronic. Okay, so just be lots of information on there. So if you lose power, you lose indication. Whereas the old days, at least they had mechanical analog gauges, they would still work. You might have to tap them a few times to get them to work, but yeah, various bits and pieces. Okay, other parts that FADEC might mention, again, just examples for background knowledge, is auto start and FADEC engine. On the engine panel, you have 115 volts. Again, watch out for bits and pieces. We're not going to go through all those because it's more type specific to a certain aircraft. It is an example, so really you should be asking a question on that. A couple of notes I'll maybe look through is oil level in the oil tank can go down by 1.6 US gallons during a start, so just be aware when an engine is stopped, oil will drain back into the tank. Yeah, some will be in the system. So once the engine starts, the oil fills the system up again, so you can drop oil level by about 1.6 gallons or 1.5 gallons thereabouts. Anything else in there? Engine operates at stabilized ground idle only when there's positive oil pressure indication. So yeah, if it doesn't have positive oil pressure indication, that's below certain oil pressure, I'll probably shut down. Okay. As usual, recommend that engine operates for at least idle for a minimum of 2 minutes before you increase to high power. So let the engine stabilize. You've warmed the engine up for at least 2 minutes. Then you can go to high power settings. And likewise, if you've been at a high power setting, okay, bring it back to idle and leave it for at least 3 minutes before. Now, it says sort of minimum of 3 minutes, but if you're in a hot environment, it will cool down, but then it could start to increase the heat because of the hot climate, depending on where the country are. But allowing to sit for 3 minutes allows everything in the engine to stabilize temperature-wise, because you've got high flowing air coming into the compressor, which will be quite cold. Hot temperature at the back end, so by come back to idle, it lets the temperature just spread out nice and evenly according to position. Fuel system, said already, is commonly linked to the P3 pressure, causing the fuel filter burners to reduce as the pressure increases. So any excessive pressure from P3 will be linked to your fuel system, and that should automatically reduce the fuel accordingly. Okay. Engine operating limits. What was one of the most critical limitations on any gas turbine engine? One of the most critical limitations. So which component is obviously critical, but it goes through a lot of stress?
Turbine.
Turbine, before the turbine?
Compressors.
No, that's too far. just before the turbine.
Then there is combustion between the compressor and turbine.
What's between the combustion and the turbine?
Nozzle guide vane.
Those guide vanes. Yeah, remember the PEM materials, they're subject to high intensity heat. Yeah, so one of the most critical limitation any gas turbine engine is the temperature of the gas entering the nozzle guide vanes. Once it goes to the guide vanes, yes, got a turbine. So the turbine is the lowest life module. Remember, it's got the lowest amount of working durable hours. After so many hours, it will have to be replaced. Even if it's working, it will have to come out because it will be getting close to its tertiary life as well, from the cold to the hot to and so on, and speeds. The poor little turbine goes through a lot of abuse. Okay, so it's the shortest life module. It's worth making a note of that one. So the turbine is the shortest life module or component. Good. What's the main limiting factor?
Is it turbine or is it nose guided vane? The lowest life.
It's the turbine. Because the NGV, although it gets very hot, it's not spinning. So it's not got centrifugal force. The next highest component is your turbine. It's getting the heat, it's getting the stress of the gas hitting it, and it's getting centrifugal forces going through. It's also getting back pressure coming through. So it's going, help me. You know, it's working very hard. So the turbine is your least life module. Right. You probably find that nozzle guide vanes can stay in a lot longer, even if they're damaged. You can lose some nozzle guide vanes and still keep in service because they're not rotating, but certain turbines can only operate for so many hours, all dependent on the type of engine. Okay, so that's the one you want to remember. It's the turbine is the lowest life module. In other words, the least amount of hours. Okay, so when we're looking at technical abbreviations, EGT is the most common one we'll look at. You can get TGT, TBT, TIT, JBT, TET, lots of T's, yeah? And lots of cups of T's as well. But EGT, sometimes they call it exhaust gas temperature or engine gas temperature, but it means the same thing. And we've got some examples, again, of graphs you must follow. If you've had a high EGT scenario, it all depends on how long it was in there. So again, you would ask the pilot, or indeed yourself, you might have noticed that during a ground run, whoa, that went too high, and you check how long that was in there for. As a ground runner, you would bring the throttle back. If you see it overswing, because you will get, during engine start, let's say, just for sake of training purposes, the temperature was 600 degrees maximum. You start the engine, it goes to 610 and comes back. That's normal, okay? A slight overswing and then comes back, that's purely normal. So don't panic if you see it going 600, oh, it's gone above 600, it's just done that and then settled back. That is completely normal. It's when it goes to 600 and keeps going, and keeps going, you're going to go, oh, got to do something with the throttle. Or it might overswing and stay at a certain temperature setting. And again, if you're not quick, seconds can go very quickly, okay? So the longer you don't notice that, one of the main things you're watching when you're doing engine start is your EGT and your RPM. Because when you start an engine up, you'll see the spool speed reaching up, and on average, roughly about 21% NH, you will open your throttle, and then all of a sudden, it'll be going slow, and all of a sudden it'll start to speed up very quickly. And that's the same time as your RPM gauge is speeding up, your EGT is going very fast as well. So you've got eyes going all over the place. When you first do one for real, it is quite holding your breaths and that, but remember and breathe, don't panic about it. You will have done all the training in the simulators beforehand, so lots and lots of hours of training simulator, and they will also give you or put you through the worst scenarios where what happens if that breaks, or what happens if that does that, emergency shutdowns and all that sort of thing. So you do all the training for all the eventualities that could possibly go wrong. So again, don't panic about it, but it's good fun. Once you get to run an engine, you've got control of the engine. You know, it's quite good fun. I had the bonus being a military aircraft, we had reheat in the back, so we could throw some extra fuel in there. All right, other limits we're looking at, obviously RPM, spool speeds. Again, you're watching all that I just mentioned there. Thrust limiting. I said we mentioned that. Common link to P3. So if you put too much thrust in the engine, we can cause too much of a back pressure. Too much back pressure, then we can stall the compressor, surges, and so on. Turboprops, propeller engines, too much thrust, too much torque, too much twist on the rotors, and stress on propellers, and again, cause a lot of damage. Okay, oil temperatures. What was the high oil temperature number again? In excess of?
124.
124, yeah. It will cause damage to rotating parts through good old oxidation. Again, with the graph there, that showed you some examples what would happen or to fall. Give me some examples of various types of engine health monitoring. We've got 1, 2, 3, 4, 5.
Yeah, with that magnetic chip detector,
Yep.
oil filter, SOAP, vibration monitoring device, and integrated data system.
Yeah. What was the big other one in between that? Sounds like a James Bond film. Spectrometric oil analysis program. Soap sample. Yeah, soap sample. Spectrometric oil analysis program. Yeah, good. I think in the old book we describe it a bit more in depth. We just give it a light mention at the moment because we didn't go that deep before. But as a background, soap sampling is, as I say, we burn the metal, we burn that sample of oil, and that metal will burn off, give off a light, because when you heat something, you burn it off, gives a light. It'll give a wavelength, and that wavelength will have a specific frequency or amplitude, and we can check that against the graph, and the computer will tell us what that material is. Yeah, so different lights, different colours. All right. What was the oil debris monitoring system, or DMS? What was the basic principle behind DMS?
Once the chip detector detects a lot of debris,
Yeah,
it will give the early failure notification or detection.
yeah. Basically, the more debris it builds up on it, once it gets to a predetermined level, it will give us a signal to the computer and say, oh, that's not right. We need to do something about it. It also does a few functions. Again, we don't go too much into it, but just a quick recap. It removes air from the engine scavenged oil mixture. It controls the breather air pressure from the engine oil tank, catches, retains the magnetic particles, larger than 0.13 milligrams. So, I mean, 0.13 milligrams is not very big, but certainly in an engine environment, that's quite big. Anything smaller than that, the NDCs will pick up those, and reports to engine electronic control contamination in the scavenge system. Okay. The filters, the oil filters, you find the coarse ones tend to be found, as it says there, just before the oil tank. Then get high pressure ones in the HP system, and then get the last chance filters, the very, very fine ones, just before the bearings. Again, it's all parts of health monitoring. The only difference with the last chance ones that we covered a few days ago is you can't really take them out until the engine comes out and goes back to an engine bay. But we can use them for health diagnostics. If we had debris on a magnetic chip, and then we shut the engine down, we'll take these filters out, we'll have a look at those and think, oh, that's why the bearing's damaged, because there's been some debris that's potentially gotten past the filter, and sometimes the filters can break. The actual gauze can actually rip open, there's maybe a big bit of debris hit it, and that debris can get into the bearing. So it might not have been the bearing's fault, it could be something that's maybe gone past a filter, okay, just that it's broken. Yeah, vibration monitoring, pretty straightforward, like we mentioned already. You have a warning lamp on the cockpit up to a predetermined level. Again, you'll see the vibration going up and down. That's your ground run. On the older gauges, it was just a needle. On the newer aircraft, your ICAS system would be a light going up and down. It'd be constantly going up and down like this. And then eventually, if it hits a predetermined level, light will come on, warning to the cockpit, warning to the pilot, and say, right, you need to check that. Yeah, age system, aircraft integrated date system, monitoring all parameters, that get recorded, so you can download the information. Old days, it was on magnetic tape. Again, it tends to be all done on computer now. And it can download it as it flies over aircraft, flies over airports as well, which is all good fun. Vibration limits, typical examples in microns for installation. How many microns at installation?
25.
During normal operation?
50.
Yeah, and single increase, you've got the maximum increase
Right.
of
20.
20, yeah. There is an example in the book. We'll quickly go through it. It's nothing too much about it. It gives you an example of what might happen. It says an engine has an installation vibration of 15 microns, which experiences a sudden increase of 40. So that will be 5 microns out of limits, because 40 and 15 is 55. Well, normal operation is 50. So out of limits, even though it's below the overall maximum permissible limits of 50. Okay, so it's just slightly out. Okay, oil systems. We can record consumption on the graph. So as you put however many litres, 1.5 litres, 1 litres, you'll make a little graph in the book as it goes along. And you can see straight away by joining the dot. It basically is join the dots. You'll put a mark in the book, depending on the date. Next day, you put another mark, and you should get sort of an average line. But you might find that the line starts to go up and up and up. And that gives you a little bit of analysis. Okay, we're getting to a point we're starting to lose more oil. Now, it could be simply it's just an engineer that's been putting the wrong number in. You know, he's maybe put 1 litre in, he's marked it down as 2 litres. If you get a spike in a graph which suddenly changes, that good indication somebody's put the wrong figure in. It's easily done, and it's come back to normal. If it's continuing to get higher, then that is an indication, yes, we are starting to use oil. But a spike in oil consumption, that's probably the engineer at that time just put the wrong number. It might be night shift, got a bit tired, whatever. Okay, so you can sort of not ignore them, but just keep an eye on it, see if it happens again. Debris from your chips, your filters, your strainers, your soap samples, again, all can be recorded. I showed the example in RIPS. Again, that's just a military example. You will have something similar for your specific aircraft and engine. Just to give you an idea of what happens in real time. Okay. Yeah, good. Okay, that was a nice little recap. What time we're now? Oh, good. Right. I think it's time for some food. Yeah? Nice bit of the day. Get some food. Okay, guys. Any questions before we head off for some food?